Next, we're going to shift gears just slightly, and we've been talking about encryption and decryption for quite a while, and that's kind of the mathematics of working with numbers to hide them and disguise them as other numbers. Now, in a lot of the times what we end up with is plain text, like a message we see in English, and we want to convert that into something where we can do mathematics, and that's the idea of encoding, where we can mathematize the English language, for instance, that we see, so that we can do math with that code, and then reverse it by decoding. And so one thing that, or one encoding scheme that is very, very common is ASCII, and it is an acronym, American Scientific Computing, da da da. You can Google it, okay? And so in ASCII, what typically happens is, and we can Google it, and so I'll pull up the table here. So what you see in this table are the different characters that we would see, and then, so like, for example, the capital A in this scheme can have these representations, and specifically, if we look at the decimal association, its decimal association is 65. So then what we can do is, instead of using A, we can use 65, and then any instance of 65 that we would see, we would translate that as capital A. And so the idea of this is, computer scientists have used this in the past, where we take the number, and then the number of characters in the ASCII table is very purposeful. If you include the extended ASCII table, it does have 256 characters, going 0 through 255, and that is very useful because that's also known as 2 to the 8th in mathematics, or 256 is 2 to the 8th, and so then we can represent each character in ASCII uniquely in terms of its bits, a binary digit, and so binary is mod 2. So all we have to, or not necessarily mod 2, but every bit is either a 0 or a 1, and then all we have to do is represent the number, so like that's 65 for capital A, in base 2. And then just note that if you have any extra space, we add zeros to it. Okay, so in the ASCII table, if you just want to double check this or see how it works, what we can do is look up, if we just want to encrypt high, for instance, capital H is 72, and then lowercase I is 105. So then coming back here, so we know that it's 75 and then, or 72 and then 105, and so this would encrypt. So this is 72 and this is 105. So then in ASCII, what we would see, if we also did it in terms of bits, this would be 0 1 0 0 1 0 0 0. Okay, and then that would be kind of the boundary of the first one, but we wouldn't actually see it ending. It would just continue on. So this would be the H in base 2, and then 0 1 1 0 1 0 0 1, and this would be the lowercase I. And again, this is the binary representation of that 72 and 105 respectively. Okay, and so then, is this a successful crypto system? Well, alone, very easy to encrypt and decrypt, but without doing any operations in it, extremely vulnerable, right? It's like if you intercept something in ASCII, right, in this base, or if you intercept a bunch of bytes, then all you have to do is say, okay, well, chunk it every 8, translate each chunk of 8, and boom, you're done. So this is new. So what they said to make this better is, we're going to include a new operation, and it's called exclusive OR, and the textbook uses a circle sum for this. I don't really like it, but we'll go with it. Mainly because this is used in theoretical mathematics to mean something different. So the idea is that what this does is it focuses down to the bits, so each binary digit, and then it says, okay, if they are the same and you're adding them, return a 0, or if they are different, do a 1. Really, it's just the same as doing mod 2. Okay, so add them, mod 2, boom, done. Okay, and so then if we were to add these two, so these are not bytes yet, but just to illustrate the point here, we would have 0, 1, 1, 1, 0. Okay, so we're doing this byte or bit at a time. Okay, and so then the idea with this is that this addition of, or this inclusion of the operation does make it so that you could send a message securely, because how do we know? So if we know, so for instance, if we intercept C circle C prime, okay, so we this is the message, so this is maybe like a C double prime. So we intercept this and we know it's a combination of two messages. Then we know that we would have to take, well, so this could be represented as a key plus one text, or it could also be a key plus another text, or it could be the sum of the two messages. So it's a little difficult to know what we're actually finding if we want to separate it out, because if you can imagine, if you are given this, there are many different things that could add to this, but we could translate it back as one of this. It could be something different. The two messages could be reversed. They could be in opposite order. I don't know. But you could make it a little bit more challenging. But if we had many of these, so I'm thinking like through those properties of a successful crypto system. Okay, so certainly the first two are easy. This one is, I don't know. This one is still questionable to me. But if you end up having many of these, then or a series of ciphertext and plaintext, then this fourth one is where this whole ASCII system falls apart. But if you maybe use this a few times, so if we take 4 out of the equation, that is actually okay. And when we do that, if we take the equation, or the fourth step of the crypto system out, and we maybe only use this once, we get something called a one-time pad. Because literally it's made so that you use it one time. So in that sense, if we use it once, great. Twice or more, that's when we start to introduce vulnerability into this system. All right. So a little bit about ASCII and addition mod 2. And we will continue in the next video talking about asymmetric ciphers.